Dear students, I have already explained what is Riemann integration and also some problems on Riemann integration. Now continuation of that Riemann integration. Now I give a statement of Darboix's theorem. These two theorems are very important. We consider only statements of these two theorems. And these theorems are used to prove many theorems. First theorem is like this. For every epsilon greater than 0, there corresponds delta greater than 0 such that for all division D whose norm is less than or equal to delta, norm is less than or equal to delta, the upper sums, set of all upper sums is less than a to b bar fx dx plus epsilon. We know that a to b bar fx dx is upper integral is defined as infimum of this capital S D. Infimum means least upper bound. A to b bar fx dx is infimum of SD, but this SD is less than a to b bar fx dx plus epsilon for all division D whose norm is less than or equal to delta. What do you mean by norm of the division? Norm of the division is it is length of the greatest subinterval. Length of the greatest subinterval is called norm of the division. To begin with Riemann integration, we have considered this closed interval is divided into number of subintervals, n number of subintervals, and one of the R subinterval is denoted by delta, and its length is xr minus 1. Suppose the length of this interval is greater than all the subintervals, then the norm of the division is length of the greatest subinterval. Now see the theorem. Once again, statement is like this. For every epsilon greater than 0, there corresponds delta greater than 0 such that for all division D whose norm is less than or equal to delta, capital SD is less than a to b bar fx dx plus epsilon. And second theorem is, this is first theorem. Second theorem is for all division D whose norm is less than or equal to delta, this small sd is greater than a bar to b fx dx plus epsilon. What do you mean by small sd? Set of all lower sums. And a bar to b fx dx is, it is the supremum of set of lower sums. Supremum means least upper bound. But a bar to b fx dx plus epsilon is, it is less than small sd. These two are called Darboix's theorems. And in your syllabus, proof of this is a theorem. These two theorems are not there, but we make use of these two theorems while proving many results. Now, next theorem is, this gives or this suggests alternate definition for Riemann integration. Now the theorem is like this. If f is bounded, function f is bounded and integrable, in a closed interval AB, then for epsilon greater than 0, there corresponds delta greater than 0, so that for all division D whose norm is less than or equal to delta, norm D is denoted by this. Norm D means length of the greatest subinterval. Suppose length of the greatest subinterval is less than delta, we have for every choice xi r belongs to xr minus 1 xr, mod of f of xi r into xr minus 1 minus I means here let us take minus a to b fx dx is less than epsilon. So this theorem suggests an alternate definition of Riemann integration. See the theorem, this suggests alternate definition for Riemann integration. How do you define Riemann integration? If a to b bar fx dx is equal to a bar to b fx dx, upper integral is lower integral, then function is said to be Riemann integrable. Now the theorem is like this. Suppose f is bounded and integrable over closed interval ab, then for epsilon greater than 0 there is correspond delta greater than 0, such that for all division of ab whose norm is less than delta, there exists xi r belongs to xr minus 1 xr, such that this less than epsilon. Now we prove this. To prove this, we directly apply the Darboix's theorem. Making use of Darboix's theorem, we can easily prove this. What is first condition given? First is fx is proof of the theorem. Proof of the theorem. Since f is bounded and integrable over ab, we have a to b bar fx dx is equal to a bar to b fx dx, and this is common, is denoted by a to b fx dx. Since it is integrable, a to b bar fx dx is a bar to b fx dx, each is same as a to b fx dx. Now let epsilon greater than 0 be any given number. By Darboix's theorem, see now we apply Darboix's theorem. Darboix's theorem, what does first theorem states? Capital SD is less than a to b bar fx dx plus epsilon. Correct? Capital SD is less than this. Since a to b bar fx dx is same as a to b fx dx, as the function is integrable, a to b fx dx plus epsilon. Take this as 1. See, Darboix's theorem is like this. First theorem, capital S is less than a to b bar fx dx plus epsilon. But since the function is integrable, in place of a to b bar we have taken a to b fx dx. And what is second theorem? Small st is greater than a bar to b fx dx plus epsilon. But a bar to b is same as a to b. A to b fx dx plus epsilon. This is 2. So by Darboix's theorem we have capital St is less than a to b fx dx, small st is greater than a to b fx dx plus epsilon. This is 1. This is 2. Now, say I write like this. Let xi r belongs to an arbitrary point, belongs to xr minus 1 xr. What is this? Arc subinterval. This D is one division of AB. It is like this: xr minus 1 xr, so on xn. By these points we have divided AB into n number of subintervals, and one subinterval is xr minus 1 xr. AB is divided into this number of subintervals x0 x1 x1 x2 so on xr minus 1 xr xn. Now psi r belongs to r subinterval xr minus 1 xr. Then small st is less than or equal to sigma r is equal to 1 to n f of psi r delta less than or equal to capital ST. See the definition of small st. Recall that one definition. What is small st? Small st is sigma r is equal to 1 to n small mr delta. Small mr means it is lower bound. Small mr is lower bound. Therefore, for any given f of psi r, mr is less than or equal to f of psi r, and capital Mr is greater than or equal to f of psi r. See, using this definition, small st is sigma mr delta, and this small mr is less than or equal to f of psi r because it is the lower bound. Therefore, we have small st is less than or equal to sigma r is equal to f of psi r delta less than or equal to capital ST, because what is capital ST? Capital ST is sigma capital mr delta, and capital mr delta is greater than or equal to f of psi r for all psi r. I think you followed this one. We have this. Now take this as 3. This is 3. Say 1, 2, 3. Now from these 1, 2, 3, what we can write? From 1 to 3, we can write like this. Small st is less than greater in this second Darbox's theorem we have a to b fx dx minus epsilon. So from 1 to 3 we have integral a to b fx dx minus epsilon less than sigma r is equal to 1 to n f of psi r delta less than a to b fx dx plus epsilon. A to b fx dx plus epsilon. Say what does 1 gives? Capital ST is less than a to b fx dx plus epsilon. Small st is greater than a to b fx dx minus epsilon. Now combine 1, 2 and 3, but from 3 we have sigma f of psi r delta class between small st and capital ST. So you can easily understand from 1 to 3 we have this. Now what does this implies? From this we can write mod of sigma r is equal to 1 to n f of psi r delta minus integral a to b f of x dx is less than epsilon. Now how you can write this? Because you know that a minus delta less than x less than a plus delta implies mod x minus a is less than delta. We have used this inequality. A minus delta less than x less than a plus delta implies mod x minus a is less than delta. Correct? So this is important. What is the theorem therefore? If the function is fx is bounded at integrable Then for epsilon greater than 0 there exists delta, so that for all division whose norm is less than or equal to delta, there exists psi r belongs to this xr minus 1 xr, so that sigma 1 to n f of psi r delta minus a to b fx dx is less than epsilon. Now this theorem suggests an alternate definition. Alternate definition for Riemann integration. Alternate definition. So what is the definition? What is the theorem? If the function is integrable, then sigma 1 to n f of psi r minus delta minus a to b fx dx is less than epsilon. Now, what does first earlier definition states? If the function is integrable, then a to b bar fx dx is same as a bar to b fx dx. Each is same as a to b fx dx. Therefore, the alternate definition is, if the function is integrable, definition for Riemann integration. Alternate definition is like this. If a function fx is integrable over ab, alternate definition is like this. A function fx is integrable over ab. Function is integrable over ab if there exists a number I, and to every epsilon greater than 0 there corresponds delta greater than 0, such that for all division d of AB, all division d, it is like this, of AB, whose norm is less than or equal to delta, and for all psi r belongs to xr minus 1 xr, sigma mod of sigma r is equal to 1 to n f of psi r delta minus I is less than epsilon. A function is integrable over AB if there exists a number I such that for all epsilon greater than 0 there exists delta greater than 0, whose norm d is less than or equal to delta. There exists psi r belongs to xr minus 1 xr such that sigma 1 to n f of psi r delta minus I is less than epsilon. Then fx is integrable, and the number I is called the integral of fx over a. Go through the previous theorem that gives alternate definition, but now this topic is very important. Condition of integrability. How to prove that function is Riemann integrable? We have to take lower and upper integrals, and if they are equal, then it is Riemann integrable. But now this theorem gives sufficient condition for function to be integrable. In this video I give only statement. Next video I will give the proof of this, and the proof is important, very important theorem it is. And we apply this theorem to solve many problems also. What does theorem states? The necessary and sufficient condition for a bounded function f is that to every epsilon greater than 0, for every division d whose norm is less than delta, the oscillatory sum is less than epsilon. What do you mean by oscillatory sum? Oscillatory sum means consider SD minus SD. You know what is SD? Upper sums. Small SD is lower sums. Capital SD minus SD is sigma mr minus mr delta. Because what is capital SD? Capital SD is sigma r is equal to 1 to n capital mr delta. What is small SD? Small SD is sigma r is equal to 1 to n small mr delta r. Now what is SD minus SD? Therefore, capital MR minus MR delta R. And this is called, this SD minus SD is called oscillatory sum. Now, the what does theorem states? Necessary and sufficient condition for a bounded function fx is to be integrable is for every division d whose norm less than or equal to delta, the oscillatory sum is less than epsilon. This capital MSD minus SD must be less than epsilon. What do you mean by necessary condition? Necessary means suppose the function is integrable, then oscillatory sum is less than epsilon. Conversely, sufficient means suppose the oscillatory sum is less than epsilon, then function is integrable. Integrable means taking sufficient condition means suppose omega d is less than epsilon, omega d is called oscillatory sum is less than epsilon, then we prove that a to b bar fx dx is equal to a bar to b fx dx. This is converse. I give the proof of this theorem in the next video. This theorem is very important. You can definitely expect this theorem for the examination. State and prove necessary sufficient condition for integrability of a bounded function fx. Sometimes the statement may be given. In the examination you may get directly the statement. This is the statement, prove that. Proof I explain in the next video. To prove this, we have to use the again Darbox's theorems. Using Darbox's theorem, you can easily prove this. And the complete notes, as I told earlier, I give the complete notes of this in the PDF form. You will be provided complete notes. Only first go through the videos, then you can refer the notes. Okay, bye. Thank you.